All right, if we could make a start, please. So, in this first talk, A Schenk is going to carry on with the next installment of use of IPLT in diffraction processing.
Okay, good. Do you all hear me? Is the microphone on? Okay, good. Okay, so I'm now going to talk about the diffraction merging in IPLT. This is the second part of the processing from what we had before. So this diagram you already know. Morning we were here, up this one arrow, and now I'm basically trying to cover here all the rest. Not the phasing. This will be afterwards another talk by Rich. So just scaling, merging, discretization of the diffraction data. Okay. So this you also already know. Here, what we need for the diffraction merging is here. Basically, you can set the parameters that are globally. You have a button to merge data if you just want to let the computer run and do it. There are afterwards ways where I can show you where you can more tightly control what you do. That's in here on the third page on the merge. So if you now switch to the merge page, it looks very similar to what you saw before for the individual diffraction patterns. You also have on the left here, you have a grid where you get a list of all the merge directories, so you can have more than one merge, because often you want to try things out. You want to see, okay, perhaps a different set of images you merge, or you want to play around with the parameters, and then see if it gets better or not. So there's an option to get the different merge directories, and you also get then some feedback on how far they are merged. So if the scaling was done, if the refinement was done, if the lattice line fitting was done. And you can also do that in more rounds to basically improve the refinement. Here in the center, you have a very similar panel to what you have on the project and diffraction pattern page, where you can set specific parameters just for the active merge. So if you want to set it for all the merges as default parameters, you can do it on the project page. If you want to set it just for that one merge you're now working on, you can set it here. Very similar to the other pages here on the right, you also have the individual steps you can do for the processing. So you can create new directories to get a new merge started. You can scale your data set. You can check the scaling, then do the refinement, do lattice line fitting, and check everything, and then you can go on and do it in the second round if you want. And here in the lower right bottom, you get similar to the diffraction pattern page. You get a set of log files where you can have a look at the results. So I probably can go very fast now in the next few slides, because this was already covered this morning by Pea and also by Anji. So but it's important that you keep in mind that here, if you have a 2D crystal, that in the third dimension we don't have discrete spots, but we have lattice lines, which basically you sample based on how your crystal was oriented, how the crystal was tilted. You sample different spots here on these lattice lines. And in general, basically, you get for each crystal you record, you get here one data point. Normally it's then more afterwards because you have a symmetry. So once you symmetrize, you normally get more than one spot then on the same lattice line. Yeah, and you have you also have heard of that. You have a missing cone. So depending on how high you can tilt in your microscope, this might be smaller or bigger. With current microscopes, it's 70 degrees, so the maximum tilt, so the missing cone is not that big anymore. Okay, so this was also already shown in the morning. So the way we explain the lattice line Fourier space is probably easiest if we start out with real space and see what we have there, and then just look at the corresponding Fourier transforms. So you have basically a continuous function. Okay, this would now be the z-axis. This I have to say. You have continuous function. If you work with digitized images, you have discrete samples of that. So that's basically a sample you have in real space, which has a certain thickness and a certain sampling. Now what we imagine is that conceptually what we do is we basically say, okay, let's do the same thing that you would have if you would have a 3D crystal. So you basically repeat it in the Z dimension, and then we multiply it by a rectangular function to get really a sample which has, in the end, has some information here, and it's 0 outside of that. So in real space, you would multiply these two. So this means we can also, if you worked in Fourier space, you can go to Fourier space, to Fourier space representation of these two, and then just convolute them. So this was also already said in the morning. So you have here is a sinc function, sin x over x. And here, these are basically discrete spots you have in the real space. You also get some set of discrete spots with, okay, that's now with red and yellow, a real and imaginary part, or you can also express it as an amplitude and a phase. So you just get the set of complex values. And then if you have lattice lines, if you do the convolution, so you basically get a set of sinc functions for every data point, add them up, end up with a cumulative cumulative function, which describes a lattice line, which also has some real and imaginary components. If you now record diffraction patterns, it's a little bit different. So the difference is that you don't really measure the amplitudes and phases or the real and imaginary parts, but you measure the intensities of this of your individual diffraction spots. So basically measure the squared function of this here. So this has some consequences. First is you have just intensities, you lose the phase information. So you cannot directly go back from diffraction data to real space and get an image. And this also means that in the end you have to get some phase information from somewhere, either by molecular replacement, as Rich will show you later on, or by recording an image data set and get image phase from there. And the other thing is, yeah, I mean, that's also true for amplitudes. You get a data set which is always positive. So your amplitudes or your intensities you measure should never be negative. Okay, so if you now measure the data, you have different diffraction patterns, different tilt, different orientation. In general, basically every diffraction pattern, always the same index, gives rise to one data spot in these lattice lines. So basically for every lattice line, you have one spot from every image, excluding symmetry. If you have symmetry, it's more. Second thing is, what you have to be aware of is this measured data always has some error. So it has an uncertainty in the x direction, has an uncertainty in the y direction. The uncertainty in the x direction mainly comes from the tilt geometry. Your tilt geometry that you determine from the lattice will not always be very precise. So that's also why you have to refine it afterwards. So this gives you a certain uncertainty in the C star direction where your data point is. And on the other hand, you measure the intensity either by profile fitting or by integration, but that's also in a noisy diffraction pattern. So you will have certain uncertainty in the also here in the intensity direction. So basically here you don't know the exact position of spots here in Y. That's very important to keep in mind, because that's what you afterwards use in refinement. By refining tilt geometry, you can basically move the spots from left to right, and by refining the scaling, or if you even go a step back, by refining like data extraction, you basically change in that direction. Okay, so that's now the overview how we do the merging in IPLT. You basically start out here. So that's where we ended the end of the last talk. You have extracted your data from all your diffraction patterns. Now you try to scale them, merge them, and then get the lattice line fitted. The first thing we do is just to do a pre-merge, which is unscaled, and use that as the first reference for scaling. We do the scaling somewhat different from what is done normally in images. So we don't do a common line scaling, but we just use a weighted bin scaling, as often is done in X-ray diffraction. Next step is then basically to you can do the tilt geometry and lattice refinement based on that first scaling, or also afterwards, then once you have fitted lattice line based on this lattice line. So then you can do refinement, get the lattice line, so then you can here fit every lattice line, discretize it, and can use this and go back basically to further refine tilt geometry and the scaling to get a more exact number there. Because chances are that in the first merge you won't get a very good refined data set. Once you're happy with it, you can basically take your discretized data set, merge it, then you get the final 3D data set in Fourier space containing your intensities. Can get from that HK alpha, and here basically you go into the molecular replacement or whatever you want to do with your amplitudes or intensities. So either direct phasing using phases from images or molecular replacement. Okay, so now first step, weighted bin scaling. What we do is preliminary merge. I already told you that data sets are binned and weighted based on the sigmas of the intensity you measured before. And then we basically take the log ratio of the merge bin versus the same bin of each data set, and then we can fit the linear function. So here in the top plot you see basically the data of the weighted bins, basically data set versus the merge. Then here you see the linear fit using the log ratio. And this linear fit gives us then two parameters for the scaling. So one is basically a linear scaling, and the other one is also a B factor here. And this should then basically put all the data sets on the same scale. Okay, so that's a quick example. So if you just merge the data without doing anything, you see you get quite a coded picture. Then after scaling, you already see much better lattice line. It's still this just from a first scale, so there is no refinement yet in there. So you see it's still quite distributed, and you also have a lot of outliers. But this should be taken care of later on during the refinement steps. Okay. So then next thing is to basically fit here through a lattice line, which can be easier in some cases, very difficult in some other cases if you're at some high resolution data. Yeah. And to do the lattice line fit, what we implemented is a kind of a bootstrapping method. So instead of fitting the lattice line once, we take several subsamples of this original data set, which have the same size as the original data set, but are randomly sampled. So you might end up with the data set where some points are missing, but all points you have twice. And then we do the lattice line fitting for each of these data sets. The advantage of this is that you get a much better estimate of how well you're fitted, what the signal of your fitted points is, because it's otherwise quite hard to get precise. So that's basically a method to get a better weighting afterwards for the fitted points. The disadvantage is that it's not just one lattice line fit, it's several lattice line fits, so it takes somewhat more time. But normally it's, at least in my opinion, it's more important to have a higher precision instead of having a faster processing. And today's computers are normally fast enough to handle that. Okay, so then once you have fitted your lattice lines, you can check them in the lattice line viewer, and that's a very powerful tool. So it displays you all your data points. You could also switch on that it displays the error bar for every individual data point, but it's a little bit too confusing here on one image. And what I have to say, that's directly in the IPD graphical user interface, and this plot is also interactive. So you basically can move it around, you can zoom in, you can zoom out to have a close look at your data set. So, and you can here, you have another window basically where you can just switch to the next lattice line. So it's very easy to go through all the lattice lines and check them. And the other thing, it might sound easy or trivial. But if you have points like these here, where you have clear outlier, you can basically just click on the point. IPLT will then open up the original image, mark that original peak where this data point is coming from, and also gives you all the information about the integration and the fit. So it makes it much easier to then find outliers and perhaps find the reason for that outlier. So you don't have to track it back through log files and see, okay, from which image was now this point. This is internally basically taken care of by IPLT, so that you can directly move back to the original data and see what is happening there. There are also some error factors that are spit out by IPLT then, which are very important to give you a measure how well you merge went, how good your image is. And these error factors are also used afterwards for the refinement. One thing I have to point out here is that normally in 3D crystallography, the standard formula for error factors uses double abs. So basically it uses the absolute value of the intensity. We on purpose change that here for IPT to also allow basically for a negative intensity. I mean, you should, in a perfect data set, you never have a negative amplitude or a negative intensity. But if you're measuring in noise, it might be that you're just the noise or your background level around your peak is a little bit bigger just by chance because it's a noisy data set. And we want to keep that in. So this means also that for the lattice line fit, the lattice line fit itself will never be less than 0. But it might be that there are some data points that are below 0 if the lattice line fit is very close to 0. So we keep these in. Yeah. We have three kind of R factors. The first two are basically for individual images only. We calculate in our Friedel, so we have a look how well fit the Friedel pairs. And the second thing we put in is this was done to try to debug and see if there are diffraction patterns which have problem with symmetry. But normally, if you have a symmetry, even if you have a tilted image, you will have some zones where the points of symmetry relate, and they also have the same C star, so you can actually compare them. For a non-tilted image, it's basically it should be all the peaks, but for a tilted image, you have just very small zones where you also have the same C star. And there, you can compare these and basically use the same formula and just use here as a reference the other symmetry related points to get a symmetry NAR sim, which basically gives you some information if this pattern really fulfills that symmetry. And one thing is also this is dependent on how the tilt geometry is. So if tilt axis is off, SAR sim will also be off. So it's also a measure of basically a second verification on how good the tilt geometry determination was. The other two merge factors are calculated basically after scaling or after lattice line fitting. You have an R merge, which basically compares one data point with all the amplitudes within nearby range, or the R fit, which then compares it basically to the fitted value of the lattice line fit. Okay, so once you have done the refinement, once you have done the lattice line fit, you have to go into your refinement, because your original scaling and your original tilt geometry will not be exact enough to get some meaningful data. So we try to refine the tilt geometry and also try to refine the scaling for every image using basically these I fit and Z fit, so basically fitted position from the lattice lines. What we normally do is, if you have a data point, we normally take the same spot on the same at the same C star value as a fitted as a reference for the fitting. We also, I think this was 2 years ago, we tried that. We actually were thinking once, perhaps that's not the best idea. So actually, that's not the that's probably not the closest point of the curve to that point, to the actual data point. So we tried to find as a reference point the point on the curve that is closest to that point. The problem with that is that here in X and Y you have completely different scales. So one is C star and the other is an intensity scale. So it depends very much on how you would weight these two different scales. It would have a very big influence on what point you actually would get. So that's why we didn't follow up on that, and then decided it's perhaps not the ideal case, but it's still better to use that and just ignore that actually the point could also move in the X direction. Yeah. Also have to say is refinement is currently in IPT is still an experimental feature. So that's the part where I'm now mostly working on and also testing it with the aquaporin data set we have in the lab. So there will still be changes once I'm through there with the testing and the verification. So that's still very much work in progress. Yeah. Okay. Oh, I think I'm quite fast today. So I'm ready at summary. So we have in IPT the pipeline to merge, scale, do a lifespan fit, and discretize data set, the diffraction data set. We also have an implementation for the tilt geometry scale, tilt geometry refinement, and for the scaling refinement. But that's my current focus. So that's still work in progress. And I'm currently using the aquaporin 0 DMPC data set to basically test and verify the functionality. We already used it before in Basel on another data set. So I know that the basic refinement should work. But still, so far we don't have a final data set which was done in IPT, which went to atomic resolution. So still I have to really go through all the steps and do the verification to get the final proof that everything is really working as it should. So that's still work in progress. Okay, yeah, that's my last slide, and I would like to thank all the people that were involved. It's basically the same slide as I had this morning because it's the same people giving the data, so I don't go through all of it. But yeah, thanks again to all the people that made it possible to develop the IPT and also to test it. Yeah, and thank you very much for your attention. And I'm open for questions.
Thank you, Andreas. You got us back on schedule now.
Yep, I was running.
Any questions? Oh, now we're ahead of schedule.
Thanks. You had these two different with the lattice line fitting. If you go a few slides back, where you say here, yeah.
This one, yeah.
So where you have the Z star in one direction and the different scalings in the other. And so did you try different weights and just like what you would do when you look at it? When you look at this box, you show this one is obviously not up or down; it's to the left, and the other one is obviously. So you just do intuitively what kind of thing you think would make sense, and then try if it helps instead of just discarding the idea.
We tried it, but So we tried to have a fixed scaling factor between the intensity and C star. That's the first try. Second try, we had the second thing we tried is to have it based on the sigma we have for the C stars. So the bigger the sigmas are for the C stars, probably the less reliable it is in that direction. So it was rather than get the point further up or down. So then we would basically have a higher focus on the IFIT. Problem is, it didn't really improve the fitting. Don't know. Perhaps if one would further investigate it, there would be a possibility to do it somehow. But somehow, what we tried didn't improve really. So that's why we didn't follow up on that so far. Yeah.
Following up on the same question, because when I look at it, that if you actually to do that to that individual spots to scale differently, then it's like distorting your 3D volume, right? When you first mentioned it, I thought, well, it will make more sense. It needs to be constrained by the images.
So that you would have a constant factor by image, basically.
Right. It's basically, if you're going to scale it by image, then it seems to make sense that if you are doing so, what you would be doing is refining your tail geometry. In other words, you are refining your tail angle when you are doing so. So that's already been covered in the other way. So it probably would not make sense to separate it out in that way. Maybe that's why it didn't improve.
Yeah, this might be the reason. Yeah.
Okay, there's no more questions. Thank you very much again, Andreas. And next speaker is Richard Height, who's going to be talking about molecular replacement.